Anushka, getting ready for the examination. Rahul. Fine. These are 49. Why people are less? So today they will say that tomorrow is Shiva, we didn't come, we don't come. After Shiva, they will say we didn't come. Yeah. After they have not done it over us. They not for everyone. Okay, fine. Design. Gate characteristics of an SCR. We have an SCR, anode, cathode, and gate. Anode cathode characteristics, we have already checked it out. We have to go for gate characteristics. Gate current. Based on the gate current. See? With respect to, we are having a characteristic with respect to gate. Means we are measuring the voltage across the gate terminal and we are also measuring the current flowing through the gate terminal. Gate characteristics of the gate. Here we have two lines. One is M and N. M and N is going to be called. Check it out. What's happening? S1 and S2. There are 2 points. S1 and S2 is there. What exactly a gate characteristic will do? Gate source voltage is there, gate current is there, we are going to have Vg minimum and Vg maximum, and similarly Vg minimum and Vg maximum. Okay, between those things is what gate is going to connect. Gate is going to be connected between these two regions. With respect to current, yeah. With respect to voltage, Vg minimum and Vg maximum. As we all come across, gate directly will not conduct. As soon as you switch on the circuit, gate will not conduct. You are supposed to keep increasing the gate current. Gate current is 0.1 milliamperes, 0.2 milliamperes, 0.2 milliamperes. We already come across an experiment. Those who did the experiment of your anode cathode characteristics of your SCR. What is the current we have given? What is the current we have measured initially on the left side? We have given VGG and IG we have measured. When the design your SCR is going to conduct, when IG is being above 8.1 or 8.2 or 8.3 milliamperes. Milliamperes. Till then it was not working. Even though I am increasing the voltage across the cathode, anode cathode, there was no change. There was no change in the current. I was not getting any change in the current with respect to anode cathode current. It was not changing voltage. Once your voltage, which is crossing 8 volts, which is generating the 8 milliamperes, because 8 volts I have 1 kilo ohm resistor over there. 8 to 1 kilo ohm, you will get 8.8 milliamperes. Once you have 8 milliamperes, then only your anode cathode is going to be giving some variation in the voltage, current is also increasing. Voltage drops and current increases. Here, all of you have done that on your instrument. Gate characteristics of your SCR. Anode cathode characteristics instrument, you know, we have already repeated the last one, we did that one. What exactly you are doing? I am keep on increasing my gate current by increasing the voltage. I kept it at 7, and I raised anode cathode voltage. I am not getting any anode cathode current. I kept it for 7.5 milliamperes and keep changing. There also it is not working out. Then I increase further for 8 or 8 milliamperes. At that time, some clearing comes into the picture. Some clearing of your gate comes into the picture. That means IG minimum. Your gate will not conduct. Below the IG minimum, gate will not conduct. Similarly, as keep increasing, somebody told, sir, I was keep on increasing, sir, current is to keep on exponentially increasing, at some level, it is not dropped down. Some level does not drop down or does not saturate. So Ig minimum and Ig maximum you have to check that one. Ig minimum is here. At this level, voltage is also increasing. It's increasing. As Ig increases, voltage also increasing over there. At some point, voltage is getting saturated. It's getting saturated here. Similarly, when you go for the second point, here, this is the other one, S2 point, S1 point, this is S2 point, because due to Vg maximum. So, there it goes and finally there also it's going to get saturated. So, we need to have Ig minimum and Ig maximum with respect to the Vg minimum and Vg maximum. So, between that stage, between that area, we are going to get S1 and S2. Here, that is what the conduction area of your gate. Gate is going to conduct, SL is going to conduct. So, this is your gate characteristics of your SCM. Simple. You should know minimum maximum of both current and voltage, and you are able to draw that one. And this is the area here, between this area, trapezium, what I am going to see here, E from here to here, here to here, and here. Only this is your conduction area, we are going to call that one. Other thing, this is, it won't conduct, here also it won't conduct, it's a saturation area, we will call that. So gate source voltage, a constant, and this is load line and all, you are going to draw that one, you can draw them, and you are going to get the load line. S1, S2, wherever they are matching over there, you are able to get the load line. So Rg maximum, resistance maximum, Rg minimum, all those things going to consider. See D1, I think where is the circuit? Next page. Here. This is the D1, D2, D3. Three diodes are there. Let us see. D1 serves to limit reverse voltage applied between anode and gate. D1, what is the purpose of D1? This is the purpose of D1. In between anode and gate. In between the anode and gate, it limits the flow of the current voltage, limits the reverse voltage. D2 prevents the negative source current. D3 blocks positive gate current coming from the supply when device is forward bias. So now, whenever you are explaining about this particular question, these three lines should be in your mind. Then, with respect to that one small diagram, if D1 is restricting the reverse bias voltage across the anode and cathode, the gate and anode. What's going to happen? How the SCR is going to conduct? Those things it will be two lines you have to explain. Okay, only one line you write it is not able to marks. I'm using a D1. What is the purpose of using a D1? To limit the reverse voltage across the anode and gate. If I limit the reverse voltage across the anode and gate, what's going to happen? How exactly SCR is going to conduct? What is the output of the SCR regulatory? You should know. Similarly, D2 purpose. What is the purpose of D2? You should explain. Right, like one line you write, below that to explain. So, like all these three lines you should write, and below that one small paragraph you have to explain that. And neatly you have to draw this particular graph where it will fetch you full marks. Full marks you are going to get that. When you know what is Ig minimum, Ig maximum, Vg minimum, Vg maximum, and what is where exactly voltage comes, which axis, all those things. S1, S2, S0. These three, if you draw, if you put the line across them, that is the load line we will call it. Okay? S1 and S2, put them, you can calculate and you're going to get the load line. So characteristics, this is equations. By using the gate current of higher magnitude, it should be ensured that the pulse width, which is directly copied from the textbook as it is coming, it should be ensured that pulse width is sufficient to allow the anode current to exceed the latching current. What is the purpose of D1, D2, D3? It's been explained here. It should be ensured that pulse width is sufficient to allow the anode current to exceed the latching current. In practice, the gate pulse width is usually taken as equal to the or greater than of SCR turn on current or turn on time. So you should know T should be greater than turn on time. T should be, that is the width, pulse width. T means pulse width. It should be greater than the turn on time itself. Anything has been given here? T, no, it's not been given here. With pulse firing, triggering, if the frequency of firing F is known, the peak instantaneous gate power dissipation P maximum can be obtained. Once you know the equation, P is equal to V into I and Vg into Ig, Pg average is equal to F into T. F is your firing, that is T is your actual width of the pulse, where F is equal to 1 over T1. Oh. Yes, ma'am. Last one. Carry. Yeah. I'll do it. Where exactly? Okay. Okay. Fine. See here, pulse has been given. T is the pulse width. T1 is T on and T off both put together is T1. The duty cycle is defined as the duty cycle. You know that one. No need to explain that one. Positive means wherever positive comes with respect to the whole time is a duty cycle. Positive of with respect to the entire time, with respect to the total time is called as a duty cycle. T divided by T1 is the duty cycle. Delta is equal to T divided by T1, which is equal to F of T. You can substitute and you're able to get the answer. So I think this is what they are given. P maximum should be less than the P average. This is one sheet you're supposed to write with respect to gate characters. One circuit diagram, one waveform, that is graph, circuit diagram and explanation. Definitely you're going to get minimum 8 marks. Gate characteristics, minimum 8 marks. I think I forgot to tell you. Have you checked the question papers? Do you have a question paper with you? Ilva? PEI, not yet checked. Previous batch was having the PEI, no? You should, at least you will be having 2 question papers. At least 2 questions paper will be there. Not 2, 4 question paper will be there. Because you are the 3rd year coming into 18 scheme. Those are in final year, they are in the 18 scheme. Those are in 5th year, that is 3rd year, they are also in 18 scheme. Minimum 4 papers will be there. RSM, even same. 4 papers, if you work it also, that's more than enough. Turn on time. Triggering. One is forward voltage triggering, second is thermal or temperature triggering, and third one is radiation triggering, dV by dt triggering, gate triggering. Gate triggering, there are 3 types are there. DC triggering, AC triggering, pulse gate triggering. So, DC triggering, that is gate triggering, there are 3 types. Listen, let me take another 5 minutes. I got a call, I'll go early. See here, this diagram, once you know this diagram, useful for your theory also, useful for your lab also. You have to know what is Ig1, Ig2, Ig3. When exactly, when Ig1 comes, what's going to happen, Ig2 comes, what's going to happen, Ig3 comes. So depends on the different values, 8.5, 9.5, 10.5, 3 values we have checked over there. This is Ig0, Ig 8.5, 9.5, 10.5, just approximately I am telling. Approximately, it's not that one you should think 8.5, 9.5, 10.5 only. In the address, make go 8.5 change similarly to the 9.5 figure, 10.5 figure. So those three values you know easily identify what is the firing level and what is the voltage and also current across the anode cap. I want to measure the voltage across the anode, I want to measure the current across the anode cathode. I can easily measure that. DC triggering, AC triggering, pulse gate triggering. These 3 types of triggering you can go for it. And this also I asked you in the IA. Turn on characteristics, thyristor turn on characteristics, gate current, anode current. You are going to measure. See, gate current I am increasing, but there is no current is coming at the anode. I am increasing the gate current, but I am not getting the anode current because here it is not happening. It should set there is a triggering concept of it. 8.5 milliamperes I given. Once I given 8.5 milliamperes, then only my anode current is increasing exponentially. Until I am going to get 8.5 milliamperes with respect to gate, I am not going to get the anode current. So that is what is showing here. 0.9 Ig they are given, and it's getting, you kept constant. Then anode currents keep on increasing. At some time, it's also going to get saturated voltage. So anode cathode voltage keep decreasing. Obviously, it's going to decrease. Triggers, voltage drops, it's going to trigger. So the pulse power loss will come like this. So we are increasing. It has gate current has come here. This is TD difference. The delay time, rise time, spread time, and turn on time. These four, if you know this graph and these four, definitely you are going to get minimum 6 to 8 marks. Minimum 6 to 8 marks you are going to get that one. Turn on characteristics of a thyristor. Mechanism. There is a turn off. This we know that one already. We have got this one in the lab also. Okay. How exactly it's going to forward current, reverse current, anode voltage.